Okay, can everybody see me, hear me?
Yes.
Can you hear me
can.
there? Listen,
We
can you see
can.
me? Can someone speak up, please? The virtual
We can
people,
hear you.
Yes.
or Emily, Gabby? Okay, now in the slides, we're continuing with the book, but basically what we're going to do now is move to chapter 7 in the slides. So basically, this is the beginning of what this next chapter is about. And so what I'm going to do is essentially go through this, introduce you to the topic of waves and energy and such like that. And it should help you understand what we're going to do with this. Okay, now quantum theory and electronic substance structure of atoms. We kind of started it before regarding the nature of how these things work. And essentially, if you remember the whole concept of what we did in chapter 2, can everybody see the slides? Those of you who are distant, can you see it yet? Okay,
No.
I'm going to share the screen with you. Can everybody see? Can everybody see now?
Yes, we can.
Can someone speak up? Anna, Madeline, Paige?
We can see it.
Hello?
We can see it.
Okay. I'll just assume we have it here. All right. Basically, if you remember the basic thing of the proton, if you remember the basic thing of starting with the proton in the center and then the electron going around it, okay? And basically what we're going to be, this is called the electronic structure of atoms regarding hydrogen. So essentially we have here the whole thing regarding this. I want to make sure I'm recording the thing also. Just a moment. I'll make sure I'm recording. Okay, can everybody see me here? Can you hear me?
Yes.
Can everybody hear me?
They're saying that they can hear you in the chat.
Oh, all right, okay. All right, good. I'm glad. I don't know why I can't hear you. It's for some reason it's turned off my hearing you. All right. Well, what I'm going to do now is continue with the slides, and I'm going to share the screen again. So we'll continue where we left off. Okay. Could everybody see the slide there? Okay. As I was saying, the hydrogen, and you got the electron going around it, and basically it comes down to the nature of energy and the way things travel regarding the nature of waves and how energy goes in. Because basically the electron, essentially when it's a certain level above the atom, essentially has an orbital momentum around it, and it has energy in that because it's energy of movement or kinetic energy. Now, the way some textbooks talk about this, we would have already talked about energy, but the point is that's coming at the end of this semester, but we'll get to that later on. So I just ask you to take my word for it. The kinetic energy is very important here regarding how these things work. So, so basically the first thing is to understand the whole nature of waves and energy. And essentially here you have the wavelength, which is the distance between two identical points on from there to there, or from the trough to the other trough on the other side. You got the wavelength there, and then the frequency is the number of waves that pass a certain point, a certain thing. So the wavelength is the first part, and then the frequency is the other aspect to it. So essentially what we're trying to do now is essentially introduce you to the whole topics of energy in waves forms. So the amplitude is the vertical distance. This is the amplitude here, going from either the line to the top or the bottom to the top, depending on what you're talking about. The midline of the wave to the peak or the trough, that's called the amplitude. Now, basically, if you know about radio, if you know a radio that's in your car, does anybody know what AM means? Amplitude modulation, okay? So essentially, there's a radio wave that goes through the air, and they moderate the amplitude. It goes up and down as you go across, okay? So amplitude is the key thing related to that, okay? And essentially, you have those together. The frequency is essentially the number of waves that pass a certain point. So basically, the more waves that go past, the narrower this is. And essentially, these being very narrow, that means the frequency is higher during a certain time frame. So it's in cycles per second. In other words, going up and down, up and down, up and down as it goes through. And that's what FM is. It's frequency modulation. So they got to carry a radio wave, and they moderate the frequency, which kind of gets converted by your radio into what you hear, the music or whatever else you hear. It's really kind of cool how those kind of fits in with what you understand about the nature of the material itself. So again, it's the kind of thing where basically these things work together regarding each of these. The speed of the wave is equal to the wavelength times the frequency. And when you're talking about light, that's called C, okay, and light or energy, and essentially that's 3 times 10 to the 8th meters per second. That's the speed of light in air or in a vacuum, okay? Maxwell produced the visible light consists of electromagnetic waves, where you have electrical field component, which kind of goes up and down, and then a magnetic field component that goes the opposite, that goes perpendicular to it. And basically there is some justification for that, yes. That's the frequency, is cycles per second. That's the unit. It's up and down. It's how many times it goes up and down. It's kind of like with your bicycle. A cycle per second is 1 revolution per second. Okay. So it could be up and down. It could be revolutions per second. It's called cycles or cycles per second, and it's just given the thing of hertz. And that's another scientist was done. Now, electromagnetic radiation is emission and transmission of energy in the form of electromagnetic waves. And kinetic energy is equal to 1/2 the mass times the velocity squared when you're talking about a massive material. But when you're talking about waves, it's different. So there's an energy aspect in the waves, and there's a lot of energy in, for example, the gamma rays that you learned about earlier in the semester in the radioactivity lab about gamma rays. Gamma rays are essentially have the energy that comes off much more stronger than X-rays, essentially that's given off by the radioactive decay. And essentially that goes from the thing of E equals m times the speed of light squared. So the energy comes from the mass being converted into energy by that relationship there. So there's all sorts of different equations that fit in to the understanding of electromagnetic waves. The speed of light in a vacuum is 3 times 10 to the 8th meters per second. And all electromagnetic radiation is equal to these. Now, the homework for this is easy. All you have to do is use this form. And this will be provided on a quiz or a test or whatever else, or on the card. that you do, and basically there'll be some problems related to wavelength and other things related to that, okay? Now, when you're talking about the nature of the spectrum, yes. Sorry? Yeah. So you could use this formula, C equals the wavelength times the frequency. The speed of light in a vacuum. Right here. Okay.
Are you going to do an example problem?
Yeah, it's coming. But we're going to talk about light and other things and how that fits in, okay?
But what's the C and then E squared?
That's energy equals the mass. Energy is equal to the mass times the speed of light squared. So speed of light squared, that's the conversion that Einstein developed regarding converting mass into energy. Okay, and we'll get to that in chapter 9. I believe it's the energy chapter when coming up in the next after the next exam. Okay, but basically with this, it kind of all fit together and make more sense. Now, when you talk about the electromagnetic spectrum, you go from frequency, which is very high, to very low, and wavelength, which goes from very low, like this. This is a very small wavelength in the nanometers. Over here, it's all the way up in meters. So essentially, there's a whole lot of different things. And the frequency down here for gamma rays, 10 to the 30th power. That's got an awful lot of energy in it, okay? Whereas radio waves are down here on the other side. And then light, this is light in here, and the spectrum goes from purple all the way up to purple all the way up to violet on the other end. So basically that's in a little narrow thing, and that's what you can see with your eyes. It's just that whole little range there. Okay, and that's the visual region. Now a photon has a frequency of 6 times 10 to the 4th hertz. Convert this into wavelength nanometers. Does this frequency fall into the visible region? This is your example, okay? So how would you set that up? Okay, well, that's all right. You have a C, this is why I'm teaching you. Okay, equals wavelength times the frequency, right?
You don't have the wavelength.
Right, you're asked to convert the frequency into wavelength. So you have to get the wavelength, and the wavelength then is going to be equal to C over V, correct? Or C over the frequency. You see that? Then you just plug the values in. 3 times 10 to the 8th meters per second divided by what? 6.0 times 10 to the 14th cycles per second. Cycles per second. Okay, so per second cancels, and then you have meters per cycle, which is frequency.
So the 3 times 10 to the 8.
Meters
like
is wavelength. Huh?
3 times 10 to the 8. That's like a constant thing. Like
Yes. Yeah, it's the speed of light. Okay. Now I'll erase my bad handwriting, and then you'll see how they do it. Okay. So let's go through this example. There's the equation. And these problems are simple, okay? This section, many students find easier, and I think many of you will do really well on this third exam. So that's why I'm encouraging you not to give up at this point, okay? The second exam is the most difficult for general chemistry 1 of almost all the students I've had. And that's just because the nature of stoichiometry and putting the pieces together is very hard for everybody, okay? So essentially you isolate the wavelength there, C over V, you then plug the values into that, and you get 5 times 10 to the 8th, 10 to the 3rd meters per cycle, but basically that's the same thing as meters. That's the wavelength anyway of the wave, and it's a cycle which is just up and down. So that's the wavelength of one cycle. Okay, and that's the answer. Does everybody see how to do that problem?
How do we?
Go ahead. That's the speed of light. Yes, that's all the time, yes. And you'll be giving it to you. You just have to practice these problems, okay?
How do we know if that falls in the visible region?
Well, just look on the thing. 5 times 10 to the third meters, you look at the chart. So let's look at the chart and see where it is. Convert it to nanometers first, and you look and see where it is on the chart. This is the chart here, and it's in the radio wave area, okay, with that long nanometers. And if I go back on the slides, see right there, that's the slide.
How many nanometers are in it?
1 times 10 to the 9th. So nano is 10 to the minus 9. Okay, so it's like it's a billion. Okay, pico is a trillion in there, or trillionth. Right here? Okay. But basically, the whole spectrum goes all the way down like this. It goes back to there, all the way.
Is that H?
What?
Is that H?
Hertz?
Yeah.
That's the unit, hertz. It's cycles per second.
No, I'm not talking about.
One hertz is equal to cycles per second. That's just the,
It's like H times V equals C. Is that H or is that?
That's
that's the lambda. It's a Greek letter. It's a Greek letter. They use the Greek letters for these, yes.
Okay, so why is it nanometers when that's smaller? Shouldn't it be like tera or gigameters? You know, because it's not -12. You know what I'm trying to say?
Well, times 10 to 12 nanometers, they just,
That's really
they just
small.
wanted you to put it into nanometers, which is 10 to the minus 9. They could put it into picometers and just say 5 picometers. But they wanted the answer in nanometers. That's why. Because it would be 5.0 times picometers. Okay, but pico is not usually the unit that wavelength is listed in. It's usually in nanometers. And you look and see if it's in the visible region. The answer is no, it isn't, because it's in the radio wave area.
Yeah, but my question is, why is the 12 not negative, making it small? You know, 10 to the
Because it's
12 is
5,000 meters. It's a very long wavelength. It's a very
Because in nanometers measure very, very small things.
yeah, I know. And so they're saying 5 times 10 to the 12 nanometers, which is the same thing as 5,000 meters. It's a 5 kilometer thing. So they just ask you to convert it into nanometers, just for the sake of this problem. Okay, because light is things, for example, 440 nanometers, that is in the visible region of light. Okay, that's kind of, if you look at the chart for where light is, 440, that's like 440, that's right there. That's a blue color when it's in nanometers, but the radio waves are all the way down here. And the wavelength here, like this is 10 to the 13th in nanometers. This is high radio waves, yes. Oh, yeah, that kind of stuff will be on the thing. So you don't have to worry about that. But what I'm going to ask you to do is work the kind of problems. That's all. And I'll give you the.
Excuse me,
I'll
Dr.
give you the
Douglas.
things like this kind of problem. That's all. It's just converting wavelength and frequency together so you understand how that works and the energy aspect in it. Okay. Yes. This is from our book, chapter 7. No, chapter 5. Okay, but it's in the Chang PowerPoints. The one that our book, the PowerPoints are lousy. All it is a bunch of charts, and it really doesn't go through the work, individual slides, the animation that this does. Okay. What? It'll be in the Chang PowerPoints thing. It'll be chapter 7. It will not be that. Okay. So basically, I'll put it there and say with notes, okay? Okay, so here you have 5 times 10 to the 12th nanometers converting it. Now, mystery one, the heated solids problem, and essentially what the heated solids problem had to do with when solids are heated, they emit electromagnetic radiation over a wide range of wavelengths. And only some of them you can see. Now, how many of you have an electric stove at home? You turn it on high. What's the color of the burner? Red. That's the color you see, but there are all sorts of wavelengths coming off, but those that you see are in the red wavelength or in the infrared. That's what heats up the thing, is the infrared as well as the heating up of the metal for the burner, okay? And so basically, the sun, that gives all the different wavelengths of light. That is also very hot, okay? But it gives them all. Now, UV radiation, of which you get sunburn from, that's another wavelength. That's at the other end of it, okay? So basically what Max Planck things essentially heated up various solids and try to detect what wavelengths would come from them. So if you have a burner that you have, that it was red and then cools down, is it still hot? No, if it cools down slightly, is it still hot? Yes, you can feel it, but it won't be red anymore. So, but it's still giving off wavelengths of light, you just can't see them, okay? So, and you can feel it above because it heats the air above the burner and you can feel it, okay? So radiant energy emitted by an object at a certain temperature depends on its wavelength, okay? Energy is emitted or absorbed in discrete units. For example, if you heat up sodium chloride in a flame, it'll become yellow. And those discrete units are called quantums, and it has to do with the energy of the electron around the thing. Now, some of you may be interested in space things, or if we talk about the Earth here, and then you put the space station up here. How do they get the space station to a higher orbit? Rockets. They put rockets to make it go faster. That makes it, gives it more energy. It goes to a higher orbit. Same thing with electrons going around an atom. You give it more energy, it'll go to a higher orbit. Okay, but it jumps with atoms. It jumps to a higher orbit. Okay, in discrete things. So essentially, it'll go from one level to the second level, and that's what Max Planck discovered in 1900, that basically heating various solids would give different colors related to that. Now, when you see fireworks, what are all the different colors you see? Those are from the chemicals in there that have been lit up, given energy, and they give off light related to what the chemicals are. Like say, for example, iron, that would be the white flash that comes from it. Copper would be the blue, okay? So it's kind of related to the lab you did when you had the copper salts and you heated it up and drove the water off. It went from giving off blue light or giving off blue light, reflecting blue light to being white, essentially. So the color changed. So energy is either emitted or it's absorbed. In the case of bodies, for example, you folks have blue shirts on or sweatshirts on. That's due to the fact that the light, all the light is absorbed that goes to it except blue, which is reflected. Okay, I have a blue shirt. All the red light and other things from the sun is absorbed by it. That's why darker shirts or darker, a black car can get really hot inside. Yes.
What are the red fireworks?
Huh?
What are the red fireworks?
Well, a different chemical. So I'll put a video up online about fireworks so you can see it too, okay?
Just like those.
Yeah, and basically they mix chemicals together and they explode them, and basically you can see the colors, and it's really the chemicals that are essentially in the firework itself.
What about the ones that change?
Well, that's because they burn at different rates and they give off different colors as they burn. Okay, so it's kind of cool, okay? But that's chemistry in action. So Planck discovered the relationship between energy and frequency. And basically, this is called Planck's constant, relating the energy and frequency with its joules per second times the frequency. So essentially, you have times the seconds, and the answer would be in joules dot second and then cycles per second. So then you would have joules related to the energy. This is energy for atoms, and it's related to the frequency in the system, and that's called Planck's constant. Okay, and
Can you go back 2 seconds?
yes, and this is in the book too. There's some problems that, and I encourage you please to read the chapter. It will be a lot more explanation for you in context, and I will put a link. I'll put a link for a good video explaining this also in the bright space.
What is JS?
That's joules dot seconds, joules seconds. Joules is the thing for energy. This is joules, which is the unit for energy, dot seconds. And again, it was not my choice to go to this before we talked about energy. It's just the way, the order that the book is used with this. Now the photoelectric effect, basically Einstein discovered this in 1905, that basically if you have light going on a surface, light going on the surface will eject electrons from it. And it's due to the fact that essentially on a surface you have an atom that has protons and neutrons in it, and you've got electrons going around. The light coming in, essentially wavelength coming in, will eject electrons out from the thing and essentially give off thing related to metals. And that's called the photoelectric effect, where essentially the light comes in there and then ejects electrons as it goes off. That happens with almost every material, but it's a lot easier with metals because they have a lot of electrons around them anyway. And that was another feature that that kind of introduced Einstein and helped them to understand what the atom was related to it. And basically this proved that light had both a wave nature and a particle nature associated with it. The wave provided the energy, the particle nature essentially provided a little bit of momentum to kind of provide a push to the electrons to leave the atom and go off. A photon is a particle of light, and you can describe as light as photons or as waves. They can be described, but they can't be both at the same time. Essentially, you have this, and here, this is the energy, and it's equal to the kinetic energy plus the work function, and the kinetic energy is the mass, 1/2 the mass times the volume squared, plus the work. And the work is the force over a certain distance. Okay, that's work in there. And that has to do with, if you have electrons that are around something, the amount of energy required to pull it away. It's kind of like you holding a backpack to your chest, and then someone coming up to grab it, to try and grab it from you. That's the force essentially that's involved. That's the work function, using a certain force over a certain distance. Okay, and it works the same way with electrons around an atom. It requires a little bit of force to pull it away, and the energy that comes from light does provide that force. Okay, and so we go back and delete the things on the slide. When copper is, when copper is bombarded with high energy electrons, okay, those are beta rays, X-rays are emitted. calculate the energy in joules associated with the photons if the wavelength is 0.15 nanometers. Well, this again is, you have the equation, and then you plug in the numbers. So the equation you're using is this. And this is very simple math. And I'm not asking you to memorize this equation. This equation will be provided for you, okay? Or on the card or on the periodic table, if I use the periodic table that has the things on the back of it, okay? And I will probably do that for the next exam, is have that other periodic table and then collect them back again that the department has a stock of. But the big thing is, what I want you to do is be able to use that question to answer the question, okay? Calculate the energy in joules associated with the photons if the wavelength is equal to that. So what do you have to do? Well, you take the values. E equals H times C over the wavelength. You plug the values in there. This is the thing from the constant, sorry. This is the constant here, okay? This is the speed of light, and this is the wavelength. And you plug those values in there associated with each one, okay? And then calculate what the math is, okay? And so basically the things cancel and you end up with joules. So it's 1.29 times 10 to the minus 15 joules, which just has to do with essentially the energy related to the photons going into that. So that's for each photon. Yes.
On the previous slide, what was the, I don't remember the equation that you wrote down, 1/2 mv squared times PV.
What? Oh, okay. Well, that's the kinetic energy. Kinetic energy is equal to 1/2 the mass times the volume squared. And the work is equal to the force times distance. Okay, and unfortunately, the way this book is, it goes to chapter 5, which addresses this stuff instead of talking about energy and energy first. But again, that's not my choice. It's the choice of the department.
Okay, and the kinetic energy is mass and volume, 1/2 mass and volume.
1/2 of the mass of whatever the electron times the velocity squared. Yes. Because there's kinetic energy in each of the electrons going through that. So basically, you just plug the values in there, and you can see how these kind of work together and calculate the joules. Now, I'll erase what's on the slide. You can see it better. Right there, okay? But again, what I'd recommend you start working on this evening is just work some problems at the beginning of chapter 5 that does the basic calculations of what we're doing now, just to introduce you to putting those equations in them. And it's just a matter of practicing the problems to get the hang of it. And please read the context of the chapter and go on YouTube, search for things about the chapter title, and there'll be plenty of ones to introduce it to you also. Okay, now, basically, if you have light that's come from a certain element, a discharge tube here, for example, this would be hydrogen, okay? It goes through a slit here. The light for the high voltage across hydrogen goes through a slit, and then it breaks into certain spectrum. There, various components, and basically that's what gives it a certain color. For example, neon light, when I was growing up, only had one color. It was just red, okay? And that basically was electricity going through that, and the element neon gives off the red color associated with this. Hydrogen is very similar to that, based on just having hydrogen in it and then doing electric through that. And the line emission spectrum of hydrogen atoms, there's 4 different light frequencies given off also. Now, if you look at street lights outside, you're working at night, you look at street lights outside, you'll notice a difference. The ones that are yellow have what are called sodium lamps in there. They require less electricity to run, and they also give off a yellow light, which doesn't kind of affect the sky affect the stars as much. So you can still see the stars when they use illumination with sodium lamps, okay? But the white light is a different chemical in the white light. For example, this is fluorescent light here, okay? There's a little bit of mercury in the fluorescent lights along with phosphorus along the glass. And basically this is a series of color. But if you were to look with a spectroscope at it, a diffractometer, you'd see there are a bunch of different colors related to the light in the lamp above. So there's all sorts of things that you may not be aware of regarding each of them. Now, the bright line spectrum of a whole bunch of different things is related to what the material is, and we'll be talking about that as we go through the chapter about where those lights come from. Okay, and so what I'm going to do now, before I go to the Bohr model of spectrum, I'm going to stop with this. I'm going to stop with this one, and then go to the other slides. Just so, just go to the other thing so you can see what our book covers now. And basically, it'll introduce it to the other aspect regarding the nature of atoms. But basically here, when you're talking about different atoms here associated with these, this, for example, is essentially the series of atoms related to the nature of the atomic radius, the size of the atoms. We really haven't gotten to that yet to explain that. But the wave properties, this is what I was just talking about in the previous slides. But again, the previous slides I was doing is a lot easier to understand than these, because these are just sample things kind of introducing it to you. The wavelength and the frequency, this may be a chart that'll be easier to understand. The wavelength is the distance between the peaks. The frequency is how many go by it. The amplitude is the height. Okay, this is another example of the spectra, okay? So basically the spectrum goes from gamma rays all the way to radio waves, with light being a very small part of it. Okay, and then you've got the relationship between wavelength, frequency, and speed going across there. And then an example problem related to that. A light blue glow given off by mercury street lamps has a frequency of 6.88 times 10 to the 14th hertz. What is the wavelength in nanometers? Well, basically you just take the equation. The wavelength equals C divided by the frequency. You plug the values in, then you get the nanometers. This one is in the range. This is the example of the range. This is in the range of what you're dealing with, okay? This is in the visible spectrum. The previous problem wasn't, okay?
Where does the 1 times 10 to the 9 on the top? It's the speed of light, and then what's the other one?
1 times 10 to the, that is the 1 times 10 to the 9th, that's nanometers per meter. They're just converting meters to nanometers, okay? Yeah, because you were asked to learn what nano was. It's just a matter of putting in, but you can put it on your card.
Is it 10 to the 9th or 10 to the negative 9?
No, 1 times 10 to the 9th nanometers equals 1 meter. They're converting it to nanometers because they want the wavelength in nanometers. But I would convert them, get the wavelength first in meters and then convert it to nanometers. Okay. And then here, some examples here of radio energy, and then you've got in phase and out of phase diffraction interference exhibited by waves. And then you've got a double slit experiment with this. But again, these slides are not in context really, and it isn't very useful to just show them here at kind of out of the blue, but that just shows the fact that there's the wave nature of each of them. And then the photoelectric effect here with the thing, essentially, they give an example of a baseball hitting a glass. It causes the glass to break. Well, with a photon hits electrons, it'll give it more energy. The electron will escape. Okay, and so basically the amount of, the number of electrons is related to the energy that's associated with this. So higher intensity light will give more electrons going off of it. And so again, they have the Planck's constant there, and it's quantized. And right now, we don't really understand what the quantization is, and I will get into that next time. And this kind of introduces the atomic line spectrum there. And I'll go back to the hydrogen atom next time in the next thing. So what I'd like you to do for tomorrow is read chapter 5, work some problems at the beginning, just practicing these certain math things. Any questions? Okay, very good. So I'll see you folks tomorrow. Do any of you distance have any questions? Anybody distance have any? I'm sorry, I can't hear you.
I do actually have a question while I look at it. Where did you get, like, why did you divide by that?
Well, this is putting it in because you're converting frequency to the C over lambda.
Okay, and that just comes
Because that
from
comes to this, yes,
Okay.
correct.
Thank you. Question, today for the lab test, do you know how many machines are going on?